Welcome to our lecture on fluid mechanics, where we are now going to investigate motion and forces that act through fluids or through gases and liquids. So the three primary objectives of this lecture will be to describe and apply buoyant force, to describe and apply drag forces, and to describe and apply lift force. So as a reminder, fluids, we're essentially talking about substances that flow or continuously deform when they're acted upon by some type of shear force. And so these can be solid, or these can be liquids, gases, and plasma. For the most part, we're really going to be focusing on liquids and gases for this lecture. So let's first start off with buoyancy force. And this is going to be an upward or supporting force that acts on an object when it is placed in a fluid. So you see this tennis ball here, you're going to have weight going down, and that's the force due to gravity, and then you're going to have a buoyant force going up against gravity. And the resultant force of gravity and the buoyancy force determines if an object will float. So this goes back to Archimedes' principle, which indicates that the size of the buoyant force is equal to the weight of the displaced fluid. So if the object displaces less fluid than what its weight is, it is going to sink. But if it's able to displace the same amount of fluid, then it is going to be able to float. Okay. This also takes into consideration the density. So in order for something to float, the object has to have a lower density than the fluid. If the object has a greater density than the fluid, it's going to end up sinking. So a tennis ball is going to sink here because the weight is greater than the buoyant force. As you can see from these vector arrows, that weight vector is greater than the buoyant force vector, which indicates that tennis ball will sink. So buoyancy is really important when it comes to ships. So a boat's going to float at the level where the weight of the boat is equal to the weight of the volume displaced water by the hull, which is below the water level. And so again, remember here, this goes back to the object density. If that density is less than the fluid density, the object's going to float. So what you see here is that they're going to have the displaced water of mass is 50,000 tons, and it's essentially going to be distributed so that however much of the boat sinks down is going to be equal to however much water is displaced. And so there's essentially two different techniques how flotation devices are used to increase buoyancy. First, what they can do is that they can reduce density. And so they can do this also by having a hollow construction. And so this hollow construction displaces water that weighs substantially more than the device. So by having air in there, water is going to weigh more than air. And so that water is going to have a greater density than the air, which means that it's going to help that object float. For humans, our center of buoyancy is located superior to our center of gravity. And the density of the human body ends up being very close to that of water. But what we find out is that lean tissues, such as muscle and bone, are going to be more dense than water, whereas body fat is going to be less dense than water. So this is why you may have heard that people with a higher body fat content are going to be more likely to float because that body fat is less dense than water. Now, with the center of buoyancy for humans, the centroid of the volume of the water displaced by an object is greater at the trunk. So the trunk makes up most of the volume, which is why we see that center of gravity shifted up, or center of buoyancy shifted up above our center of gravity. And so how does this center of buoyancy then essentially influence if someone sinks or floats? So again, weight. So you've got your weight and your buoyant forces that we're going to tend to rotate a swimmer until the forces are aligned. So you've got weight, and so if someone's sprawled out in the water, weight's acting through the center of gravity, which is inferior to the center of buoyancy, and it's going to cause this clockwise rotation. The buoyant force acting through the center of buoyant is going to cause this clockwise rotation as well. So what ends up happening is it shifts the whole body in this clockwise or direction until that buoyant force and the center of gravity are lined up vertically here. And now this is where they're going to be offset, and that's where our equilibrium is. Okay, so when you're just floating there, you'll start to rotate, and that's just happening because you have this imbalance of the gravity and your buoyant force, which then have to rotate the body until they're in equilibrium. So swimmers who are afraid to float on their back end up going into a pike position where they flex at the hip and they lift their head out the water. What this does is it reduces the buoyant force because there's now less water displaced. And then that's going to actually end up with them sinking. So by panicking like that, going in that pike position, that actually is harmful and makes them start to sink. The next fluid force that we have is drag force. And drag force is going to be the force resisting motion between an object and a fluid. This is going to act parallel to the flow of the fluid that's going in the direction past the object. So it's essentially acting in the opposite direction of the object's motion. Think about drag being similar to friction, where it's acting against the direction of motion. And there's a handful of factors that can influence it. So you've got a coefficient drag, you've got a fluid density drag, frontal area, and then the relative velocity of the fluid. So the coefficient drag, essentially a rougher surface is going to result in more drag. The fluid density, so think about if you're swimming through water versus swimming through gel. Gel is going to have a greater density, and so it's going to be harder there's going to be more drag force to try to move through that. Frontal area, the larger that front area, the more drag force there will be. And then the relative velocity of the fluid. This is essentially, think about this. If you're running in the same direction with the wind, your relative velocity is lower. If you're running into the wind, your relative velocity is larger because now you're going at 5 miles per hour. The wind's coming at you at 2 miles per hour. So that's really a relative velocity of 7 miles per hour. So here's what we mean when we say relative velocity. So it's the velocity of one object as observed from the reference of another object. So if you're running at 6 miles per hour into a headwind of 3 miles per hour, what you end up getting is a relative velocity of 6 minus -3, because it's going in opposite direction, which gives you 9 miles per hour. Now, if you have a tailwind at 2 miles per hour while you're running at 6 miles per hour, 6 minus 2 really equals a relative velocity of 4 miles per hour. Like I said, surface drag is sometimes referred to as fluid friction. It can also be referred to as skin friction drag. And this is going to be the friction force between fluid molecules moving past the surface of an object between the various layers of fluid. So you're going to have a boundary layer, which is a region of fluid that's going to be affected by the surface drag. And this, what you see here is that the fluid moves slower than regions of the fluid further from the surface of the object. So if you look at this paddleboard, this boundary layer, you see that the fluid is moving slower than it is at the this layer further away. You can modify the roughness of a surface to influence the surface drag. So by having a smoother surface, there's going to be less surface drag. Or by having a rougher surface, there'll be more surface drag. So a lot of times skis are going to be waxed, or swimmers shave their body hair or wear smooth bodysuits, some of which has been allowed. And these are all to reduce the roughness of the surface to then reduce the surface drag so it doesn't slow them down as much. We also have pressure drag, and this is going to be a resistant force to the fluid flow that is created by a pressure differential when the fluid flows around an object. And this pressure drag is going to be the most dominant drag force for many sports. So what you see here is that you've got a soccer ball, and the fluid, the air, is going from left to right, and there ends up being this kind of pocket behind the ball itself. What happens is you're going to have a high pressure in front of the object and a low pressure behind the object, which we would call the wake. There then ends up being a resultant force from going from high to low pressure, so backwards, acting against the direction of the ball, which results in it slowing down. Last, we have laminar and turbulent flow. Laminar flow is going to be fluid particles that flow relatively undistributed in parallel layers. So these are going to be streamlined with low velocity conditions. but contribute to larger pressure drag. And then you have turbulent flow, and these are going to be fluid particles that bounce off each other and end up mixing chaotically. And you're going to see this turbulent more so with high velocity conditions. It contributes to a smaller pressure drag and then a later point of separation. So what you can see here is with a golf ball, let's imagine there was one that was smooth compared to the golf ball with dimples. What ends up happening is with this smooth surface, you're going to have this greater magnitude of separation, and you're going to have a very large wake. With the golf balls, what ends up happening now is that there's going to be this turbulent layer that's built around the ball, which then results in separation occurring later and having a thinner lake. So this ends up reducing the drag for pressure to then not prevent the ball from slowing down as quickly. So this kind of chaotic buffer essentially that's formed around the ball by having those dimples is actually protective, because now it reduces the wake behind the ball, then there's less drag force. We technically also have wave drag, which you see with swimming, and this is going to be a disturbance at the surface of an object that creates waves with the fluid and that resists the motion of the object. So think about swimming. There's going to be this wave buildup in front of the swimmer, and this is going to act in the opposite direction of their motion, and again, become a hindrance. So this wave drag is really a concern in open water, where you've got this mixture of air and water creating these waves essentially in front of the person. Whereas pool swimming is going to be much less affected by the wave drag, and lane markers and gutters can actually help dampen those waves so they're not coming back and rebounding to the neighboring swimmers. The last type of fluid force we're going to talk about is lift force. And this is now going to be a force that acts perpendicular to the flow of fluid. So it's going to form a 90-degree angle between the drag and the lift force. It's not always going to act in the upward direction. So even though it's called lift, there can be a downward lift force. This is going to be influenced by the coefficient of lift, the fluid density, the frontal area, and the relative velocity of the fluid as well. And so if we visit Newton's laws and lift and how this actually goes together, what ends up happening is that air molecules are going to strike the undersurface of an object and then are deflected off the surface, or they accelerate off the surface. And what ends up happening is that there's this resultant force then. So you've got an air molecule that comes in, hits the bottom of the surface, and is going to deflect downwards. The reaction force then acts in the equal and opposite reaction direction. Okay, and this is going to be the resultant force of the lift and the drag force. So the reaction force is going to create that lift and create the drag, and the reaction force is going to be large due to many fluid molecules being deflected downward. Okay, that's what really contributes to these larger lift forces. Okay, but the big thing, so this is just applying Newton's second and third laws. This reaction force is going to be equal and opposite to the impact force, and then it's decomposed into a lift and a drag force. Bernoulli's principle plays a role into lift. And so with Bernoulli's principle, it says that pressure in a fluid is inversely proportional to the velocity of the fluid. So the faster the fluid's moving, the lower the pressure. What ends up happening here is that the lift acts in the direction from high to low pressure. So when you think about an airplane wing, the fluid passing over top of the airplane wing is going to cover a greater distance than the fluid passing below the wing. And so what ends up happening is that you have this faster velocity of the fluid above the wing than you do below, faster velocity, low pressure, slower velocity, high pressure. The force moves from high to low pressure. So you see this upward lift force. So this is how airplane wings, that's why they're kind of slanted down, so that the air above has a faster velocity, which then results in this lift force in the upward direction because there's lower pressure above the wing. So that's an overview of fluid mechanics and some of the primary forces that act in fluids, so in gases and liquids. If you have any questions, go ahead and write them down, post them on the discussion board, and bring them to class, and we'll chat about fluid mechanics again when we meet next.